When it comes to population growth, populations tend to remain constant regardless of how many offspring are born. It might seem like a contradiction, but things like natural selection are just one way populations stay in check. To really understand populations, we must explore how they grow and what factors limit growth. Let's explore two models of population growth: the exponential growth and logistic growth models. Exponential growth happens when a population is not restricted by resources or other species in their environment. The rate of population increase, noted as R, is the difference between birth rate, B, and death rate, D, plus the movement of individuals into or out of the population. Here, I is the rate of movement into the area, and E is the rate of movement out of the area. In this case, movements of individuals can have a major influence on how a population fluctuates. Take America's rising population at the end of the 20th century, for instance, which was mostly due to immigration. The exponential growth model assumes that populations grow without any restrictions, and that rates of individuals coming into and leaving an environment are equal. The biotic potential is the maximum population growth for a species under optimum conditions. Mathematically, this is represented by dn divided by dt, or the growth rate of the population, where n is the population size and t is time. This is equal to n multiplied by Ri, or the maximum rate of increase per each individual in a population under optimal conditions. The biotic potential of any population will experience exponential growth. Even when the rate of increase in a population remains constant, the number of individuals within it grows rapidly as the size of the population grows, which ultimately leads to a population explosion. Unrestricted growth only prevails for short periods, usually when an organism is introduced into a new environment with abundant resources before it stabilizes. No matter how fast the population grows, it must eventually reach a limit because of resource shortages in its environment. Think about it. If you and a group of friends were on a desert island and could only eat coconuts, eventually the number of coconuts available to you would dwindle as you ate them for every meal every single day. In the environment, as a population grows and uses up resources, some resources begin to disappear, like the coconuts, and population growth is no longer supported. The size that a population stabilizes at, which represents the maximum population size a particular environment can support, is called the carrying capacity, which is symbolized by K. The logistic growth model deals with populations that approach their carrying capacity. As a population nears its carrying capacity, its rate of growth slows due to fewer resources in the environment. In this model, the growth rate of a population, dn divided by dt, is equal to its capacity for growth, r multiplied by n, which is then multiplied by the carrying capacity that has not been used up yet in the environment, k, minus n, which is then divided by k. As the number of individuals in a population, n, increases, the fraction of resources by which r is multiplied becomes smaller and smaller, and the rate of population increase declines. If you plot n versus time, you'll end up with a sigmoidal growth curve, which is common for many populations. As a population stabilizes at its carrying capacity, its rate of growth slows, eventually coming to a halt. If a population is below the carrying capacity, then the growth rate is positive. But if the population has extended beyond the carrying capacity, the growth rate is negative. As the population approaches its carrying capacity, the growth rate approaches zero and stabilizes. Regardless of whether a population is initially above or below carrying capacity, it will always move toward that number and stabilize. So, populations that follow the logistic growth model hover around the same size. Populations are ever-changing, yet, as we learned today, remain stable at the same time. The contradiction between population change and stability comes down to each group's environment. As environments are ever-changing, so too are the populations that live there.